Welcome to the Waves and Sound review for the AP Physics test. Waves are how we transfer energy. It's how we transfer energy without transferring any mass, without transferring any matter. If there's an earthquake in Japan, the energy from that earthquake can be transferred all the way around the world through the waves in the ocean, but no actual matter can get transferred, just the energy itself. So starting out with pulses, a pulse is a packet of energy. This is what I was mentioning just a second ago, that waves transfer energy, not matter. One very important principle is that the speed of a wave only depends on the medium. The speed only depends on the medium. So, for example, if I'm sending waves through some carbon dioxide, let's say I'm sending sound waves through carbon dioxide, as long as the medium stays carbon dioxide, I know that the speed must stay the same. So think to yourself, same medium, same speed. Now, if the medium does change, the frequency doesn't change. So the frequency of a wave stays constant, even when it changes from one medium to the next. Okay, two main types of waves are longitudinal and transverse. Go ahead and try the next problem. Pause your video while you try it. Let's go through this problem. A person vibrates the end of a string, sending a transverse wave down the string. If the person then doubles the rate at which he vibrates the string while maintaining the same tension, the speed of the waves will do what? So here, the string and the tension stay the same. And what that's trying to tell me is that the medium is staying the same. And when the medium stays the same, the speed stays the same. But it also says that the person vibrates the end of the string. If the person doubles the rate, the rate of vibration, that's the frequency. So the frequency is being doubled to 2f. So let's read the choices. The speed of the waves, doubles, no. Doubles, no. Doubles, no is unchanged. It has to be unchanged because the medium is the same. And then the second part is saying what happens to the wavelength. Well, you should know that from your wave speed equation that if the speed stays the same and you double the frequency to 2f, then you have to half the wavelength to get the same answer. So the wavelength must be halved. Okay, here's some wave terms that all kind of sound the same: reflection, refraction, and diffraction. But they have very different meanings. So reflection happens when a wave bounces off of a barrier. We have two types, fixed end and free end. Refraction happens when the medium changes, which also causes the speed to change, sometimes the direction. And diffraction is when a wave spreads out behind a barrier, behind an obstacle. Go ahead and try the next 1-2 problems and pause your video while you try these two problems. You should have attempted both of these problems. Let's go through them. So one end of a horizontal string is fixed to the wall, right here, and a transverse wave is generated at the other end, moving towards the wall as shown and reflected at the wall. Properties of the reflected pulse include which of the following? So first of all, this is a fixed end. When we have a fixed end reflection, after the reflection, we get a 180-degree phase change. Okay, the amplitude flips. So properties of the reflected pulse include which of the following? It has a greater speed. Did the medium change? No, it did not. So the speed doesn't change either. So that's false. It has a greater amplitude. Greater amplitude would mean it got more energy from somewhere. I don't see anywhere that it's going to pick up any more energy. That's false. It's on the opposite side of the string. Okay, since it had a phase change, it is on the opposite side of the string. So 3 only. Okay, next one. So we have some wave fronts going through a small opening. After they pass through, they're going to start to spread out behind the barrier. This is called diffraction. They start to spread out as they go around the barrier. So, choice 4. Okay, now, so far we've only looked at one wave. When we have 2 waves, and if they collide, they're going to experience interference. Now, there's 2 types of interference, constructive and destructive. Go ahead and try the next 1, 2, 3 interference problems. Pause your video while you try the problems. Okay, you should have attempted these 3 interference problems. Let's go through them now. The diagram below represents 2 waves traveling simultaneously in the same medium. At which of the given points will maximum constructive interference occur? Okay, constructive interference. So here at point B, we have a trough and a crest. That's going to give us destructive interference. At point A, we have we definitely have 2 waves on the same side of the medium, so that will be constructive interference. At point C, it will also be constructive interference. At point D, they're both waves are on the same side of the medium, but notice that it's all the way at the amplitude. So when I add these 2 up, I'm going to have a huge constructive interference. So this is going to be my maximum constructive interference at point D. It's going to give me, sometimes people like to say, if you have 2 troughs and you add them up, you get a super trough. Okay. Here, the diagram shows 2 transverse pulses moving along a string. One pulse is moving to the right, the second is moving to the left. Both pulses reach point X at the same instant. What would be the resulting motion of point X as the 2 pulses pass each other? So, when 2 pulses interfere, they pass right through each other, and they add algebraically. So, let's think about this. Right when they reach, so here's my point X. Okay, right when they reach point X. So I'm going to have my first wave looking like this, and my second wave looking like this. So point X at first is going to quickly jump up. So I think it's going to start by moving up. And then I'm going to show, I'll label this pulse A and this pulse B. Then I'm going to show when they're perfectly overlapping. So this is when they're perfectly overlapping. I think that you can probably see that one of the pulses, pulse A, looks like this. The other one of the pulses looks like this. And they're going to cancel each other out. Everywhere that pulse A is positive, pulse B is negative. They're going to perfectly cancel each other out. So that means that point X has gone down. Okay. Then as they pass through each other, I'm going to show you right after they pass through each other, pulse A is now on the right, and pulse B is now on the left. And if you look at what the point X has done, so first it had to go up, then it went back to the equilibrium, then it went down, then it's going to go up again. So up, and then down, and then right after they pass through it has to go up again. So up, down, up. That's what that point's going to do. Okay, again we have two waves, they're passing through each other. What happens when they're overlapping? So when they're overlapping, we're going to have a wave like this being added to a wave like this. Just make up some numbers. Say this is +2, this is +2, and this is -2. And add up both halves. Okay, so if I add those up, I get on the left half, I get a +4, and on the right half, I get 0. +2 and -2 give me 0. So it is going to look something like A, where it's tall on the left half, but it's 0 on the right half. Okay, standing waves are waves that appear to be stationary. We have some terms, crest, trough, node, amplitude, wavelength that you should know. Go ahead and try the next two standing wave problems, this one and on the next page. Pause your video while you try these problems. You should have tried the next two standing wave problems. Okay, two waves of the same wavelength interfere and they form a standing wave. What is the straight line distance between the two nodes? So here's a node, and here's a node, and it wants to know what is this distance from node to node. Well, one S, so here's an S, that is a full wavelength. So if you just want to know what is it from node, and a wavelength goes from node to every other node. So if you just want to know between two nodes, that's going to be half a wavelength. Choice 3. Okay, next one's a real quick one. What shows the amplitude and what shows the wavelength? Okay, the amplitude is measured from equilibrium to an antinode. So B is an amplitude. And a wavelength shows one full cycle. So trough to trough, or if you're looking at the S's, one full S, but D is showing you a full wavelength. Okay, we haven't done too much math for waves yet. We haven't calculated much. So these are the equations that you should know. If you're trying to calculate the behavior of a wave, you can still use your constant speed equation, speed distance over time, or you can use the special wave speed equation, wavelength times frequency. Sometimes you use one, sometimes you use others, maybe you use both sometimes. And you should also know the relationship between period and frequency. They are reciprocals of each other. Go ahead and try the next 1, 2, 3 wave speed problems. Pause your video while you try those. You should have tried these 3 wave speed problems on your own. Let's go through them. A metal bar is vibrating with a frequency of 200 Hertz. So I know the frequency. And we are being asked for the period. So period is simply 1 over frequency. So 1 over 200. And so 1/200th is 0.005, and I'm not seeing that here, so none of the above. Okay, assume the waves are propagating in a uniform medium. What does that tell you? We've mentioned it many times in this video. A uniform medium means constant speed. If the frequency doubles. Okay, so speed equals wavelength times frequency. We want to know what happens. So the speed of the wave doubles, no. The speed's constant. The speed of the wave halves, no. Okay, so the choices are the wavelength doubles or the wavelength halves. So I think we actually had a problem like this earlier in the study guide. So the frequency is doubling. So f becomes 2f. And to keep the speed the same, the wavelength needs to be halved so that the 2 and the 1/2 will cancel. So the wavelength of the wave halves. Next problem. A wave generator is 4 meters from the wall, and it produces this nice standing wave. If the speed of the wave is 10 meters per second, what is the frequency? So frequency equals speed over wavelength. We know the speed, 10 meters per second. And now we need to find the wavelength from the picture. So look at count the cycles. Here's one at backwards s, so that's a wavelength. And here's another backwards s, so that's another wavelength. So this is showing us 2 full wavelengths. That must mean that one wavelength is only half that length, 2 meters. So the frequency is 5 hertz. So sound is a wave. It's a longitudinal wave. And through air it moves at about 340 meters per second. Sound requires a medium. So sound, there's no sound in space because space is an empty vacuum. Sound needs to go through something. It could be air, it could be water, it could be a railroad track, but sound has to go through something. You may see like little kids, maybe when you were a little kid you tied 2 cups together with a string and you hold one cup to your ear and your friend talks in the other cup. Well, the sound is propagating through that string, right? And so sound requires a medium. The loudness of the sound is related to its amplitude, and the pitch is related to the frequency. This should say volume. Volume, loudness, same thing. Go ahead and try this sound problem. Pause your video as you try this problem. Okay, hopefully you've tried this sound problem. A vibrating tuning fork sends sound waves into the air surrounding it. During the time in which the tuning fork makes one complete vibration, the emitted sound wave travels how far? Okay, so we have a tuning fork here. And the tuning fork vibrates, it vibrates back and forth. It moves back and forth. And that creates, when the tuning fork moves left to right and then back again, the sound wave, it has created one full wavelength of sound. Okay. So how far has the emitted wave traveled? One wavelength is looking pretty good. Okay. Yeah, it's not 340 meters. It's not proportional to the frequency. It's not, yeah, one wavelength. Okay. One cycle of the tuning fork produces one cycle of the sound wave. Okay, resonance. Every object has a natural frequency. Okay, so a wine glass has a natural frequency. A bridge has a natural frequency. It's just this natural frequency. Every single object has one. And when you vibrate an object at a frequency that matches the natural frequency, we call that resonance. And so this is the famous example is an opera singer can hit the right pitch to make a wine glass shatter. Well, what's happening there? The wine glass has a natural frequency. The opera singer is trying to find that exact frequency. And when that happens, the wine glass starts to vibrate uncontrollably and shatters. when two sound waves interfere with each other, and if the frequencies are close but not the same, we'll get a beat frequency. Okay? And the beat frequency, I'll call that frequency of the beat, is equal to the difference of the frequency 1 and frequency 2. So go ahead and try this problem. Pause your video and play it after you've tried the problem. Okay, you should have tried this beat frequency problem. It says one stereo loudspeaker produces a sound with a wavelength of 0.68 meters, while the other speaker produces a sound with a wavelength of 0.65 meters. What would be the resulting beat frequency? So the frequency of a beat is equal to the difference, frequency 1 and frequency 2. And how do we get the frequency 1? Well, the frequency 1 is the speed over wavelength 1. Frequency 2 is the speed over wavelength 2. Since it's a sound wave and we're assuming it's in air, the speed is 340 meters per second for both of them. And it gives us the wavelengths, 0.68 and 0.65. I'm going to plug those in and see what that gives us. So here I get a frequency of 500 hertz. And here I get a frequency of 523 hertz. Here's the two frequencies, subtract them, you get 23 hertz. So that's the frequency of the beat. Okay, Doppler effect. Okay, that happens. Doppler effect happens when you have an object that's emitting a sound and it's moving towards a listener or away from a listener. So say you're out at NASCAR, you're watching some cars drive by and you hear them go, right, as they drive by. When the car is coming towards you, here's the car, here's your ear. When the car's coming towards you, it's chasing its sound waves. So the wavelength gets shorter. The frequency gets higher, gets more frequent. As the car passes you, let me move this up so you can see what I'm doing. When the car passes you, the wavelength gets longer because the car is driving away from its sound waves. And the frequency gets less frequent. So that's why when something's driving towards you, you hear a high pitch. And when it's driving away from you, you hear a lower pitch. Right? As a car drives by, you hear that starts high, ends low. Go ahead and try this problem, Doppler effect problem. Pause your video now. Okay, let's go over this problem. A driver of a car sounds the horn while traveling toward a stationary person. Compared to the sound of the horn heard by the driver, the sound heard by the stationary person has. So we are driving toward the person. If you're driving towards, the wavelengths are getting shorter. Shorter wavelength. And that's a higher pitch. Okay, when the wavelengths get short, the pitch gets higher. Okay. Last thing in this unit is harmonics. So I'm going to take some time and I'm going to show you how to draw the harmonics for both a closed pipe, open and closed pipe, and a guitar string. So make sure that you have some paper available. We'll go through and try and remember how to draw all these harmonics. But there's just one tip that I want you to remember with harmonics, is that if you have a problem that's using a tuning fork, the frequency is constant. Because tuning forks only have a single frequency. The second tip is if the medium is constant, like let's say it's on the same string or it's in the same gas, then the speed is constant. So try and keep that in mind when you're solving harmonics problems. So let's go through, first of all, a guitar string. So if I have a guitar, the string is clamped down. I'm going to draw 4 different harmonics. The string is clamped down at both ends of the guitar. So at both ends you have to have nodes. So this is for a guitar string, or any string that's vibrating. So the first possible situation you could have on the string is, this is the simplest possible standing wave that you can have. And I'm gonna label, let's say that the string has a length L. The next possible standing wave you could have looks like this. Again, I have to have a node at both ends because guitar strings are clamped down at the ends. Here's the next one I could have. And let's draw one more. So here are four possible vibrations, the first 4 possible vibrations on a guitar string. The first one is called the fundamental frequency. And then this one is called the second harmonic. Sometimes people like to call this the first overtone, okay, but I usually just call this the fundamental, then the second harmonic. This is called the third harmonic, and this is the fourth harmonic. Again, this is also called the second overtone, and this is called the third overtone, just some terminology. And what we're going to try and do is we're going to write the equation for the wavelength. So here I see that the length of the string, this is for the fundamental frequency, the length of the string equals, from node to node, that's a half of a wavelength. So the wavelength, if I just rearrange this, is 2L. Here, the length of the string is a full wavelength, 1 full S. Okay, so wavelength equals the length of the string. And the next one, the length of the string is 1.5 wavelengths, so 3/2 wavelengths. Or for solving for lambda, lambda equals 2L/3. And in the last one, the length of the string has 2 cycles, so 2 wavelengths, or the wavelength equals L/2. Now, I don't think it'll bother anyone if I call this, if I rewrite this as 2L/1, or if I rewrite this as 2L/2, right, the 2's cancel, 2L/3, or if I write this, lambda equals 2L/4. Same thing, right? And so if you look at the pattern here, 2L/1, 2L/2, 2L/3, 2L/4, the formula for a guitar string is wavelength equals 2L/n, where n can equal 1 or 2 or 3 or any integer value. Next, we've got, we're going to do a open-ended pipe. So again, I'm going to do the first 4. So open-ended pipe, there's 1, there's 2, 3, 4. The pipes have length L, And I'm going to draw the first four. Now, a pipe is a complete opposite. At the ends of the pipe, it actually has to have an antinode. So we have to have an antinode at both ends. So the simplest way we can have is one antinode to another, crest to a trough. The next one I can have is skip an antinode. The next one we can have is we skip two antinodes. And the last one, we skip three antinodes. Okay. Same names as before. This is called the fundamental. Second harmonic. Third harmonic, fourth harmonic. And again, I want to write the formulas for wavelength. So for the first one, the length of the pipe has, from crest to trough, that's half a wavelength. From crest to crest, that's a full wavelength. From crest, that's a full, that's another half, so that's 1.5. So this has 3/2. And the fourth has 2 full wavelengths. The length of the pipe holds 2 full wavelengths. If you compare this to the guitar string, it's exactly the same. So we can use the same equation as we did on the guitar string, that the wavelength equals 2L over N, where N equals 1, 2, 3, or any integer number. Okay, last one. The last one is an open-ended pipe. So it's going to be closed on one end and open on the other. I might have just said that wrong. Before we just did an open-ended pipe. This is a closed-ended pipe. Closed-ended pipe. So just to label these correctly, the one we did last is called open-ended pipe, and this one is called closed-ended pipe. And a closed-ended pipe is just closed on one side. Okay, and let's call the length of the pipe L. Okay. On a closed end, we have to have a node, and on an open end, as before, we have to have an antinode, always. So the simplest wave we can have goes straight from node to antinode. Next, we skip an antinode. Next, we skip 2 antinodes. Next, we skip 3 antinodes. Okay. Now the names are a little different. This one is still called the fundamental. But this, it doesn't have a second harmonic. It jumps straight to the third harmonic, then the fifth harmonic, and the seventh harmonic. Okay, so open-ended pipes do not have even harmonics. So the length of this pipe is a quarter wavelength. The length of this pipe is 3/4 of a wavelength. The length of this pipe is 1 full and then another quarter. So the length here is 5/4 of a wavelength. And the length here is 1/4 short of 2 wavelengths. So that's going to be 7/4 of a wavelength. Solving for wavelength. 4L, 4L over 3, 4L over 5, 4L over 7. You should be able to see that the formula for wavelength is 4L over N, where N is only odd. 1, 3, 5, or 7.